Most LLM systems fail long before they crash. You need SLOs that tell you when to roll back, fall back, or send the task to a human. This is the setup you'll be able to run after this, which gates an answer against latency and quality targets, and decides when to fall back or escalate. I'm Professor Pi, teaching AI engineering and LLM systems with simple Python. LLM reliability shows up as a practical operations problem. You send queries, and sometimes the model is slow. Sometimes the model answers, but makes stuff up. Users noticed both. Success means answers that are timely and trustworthy enough for the task. Engineers solve this by measuring what matters, setting clear targets, and wiring automatic decisions when those targets break. At a high level, we use SLIs, SLOs, and error budgets. An SLI is a signal you can measure like P95 latency or task success rate. An SLO is a target you set for those signals. An error budget is the room you have to fail before you must take corrective action. Together, they let you automate rollbacks, cheaper fallbacks, or human review. We are going to build a tiny Python setup that does 4 things. It computes simple SLIs from observed requests. It translates those SLIs into an SLO and an error budget. It gates a canary release by comparing it to baseline. It chooses fallback routes and runs a small policy that allows falls back or pages an engineer. The code is intentionally minimal, so the logic is obvious before you scale it up. Now we'll compute core SLIs for a toy LLM task run. This snippet computes core SLIs for a toy LLM task run. The list lat_ms holds observed request latencies, and OK contains task outcomes as 1s and 0s. The helper function PCT sorts the latencies and selects a position to approximate a percentile, which gives us a quick median and P95. We then divide the sum of OK by its length to get a task success rate, a compact proxy for task completion. These 3 metrics together form a simple reliability view you can track over time. If lat_ms shrinks or OK improves, the printed values reflect faster and more reliable behavior. The printed values establish a baseline for latency and success. This example sets the scene. With a P95 and a success rate, you can answer simple questions about performance and correctness. Use these numbers as the raw inputs to any alerting or rollout logic. The median helps you with typical experience, while P95 protects the tail. The success rate is your minimal quality check for whether answers more acceptable. Next, we'll turn SLIs into an SLO and watch the error budget. This example converts SLIs into an SLO and a live error budget. The variable SLO-OK encodes the success target, and window n gives the request volume over which you allocate the budget. We compute aloud as the total errors you can spend, then estimate a recent failure rate from last hour recs and last hour fail. Dividing the failure rate by the error fraction yields burn, a normalized urgency indicator. Subtracting recent failures from allowed gives errors left, the remaining headroom. Raising SLOWuck tightens the budget and increases burn. Increasing window n grants more budget. The printed values show how much budget remains and how quickly it is depleting. This example turns raw telemetry into a decision signal. When burn is small, you can be relaxed. When burn is growing, you need to slow down releases, shift traffic, or activate fallbacks. The error budget ties quality targets to concrete counts so that human teams and automation share one source of truth. Now, we compare a canary to a baseline and decide if it can go live. This code ranks a canary against baseline and dates release. Two small dictionaries, base and canary, store P95 latency, success rate, and an approximate cost. The function score combines these with weights that reward success and penalize latency and cost, producing a comparable number for each variant. The variable winner selects the higher score, while gate requires the canary to meet slow OK and slow P95 to proceed. Increasing success weight favors safer rollouts. Increasing latency weight pushes for faster responses. Tightening slow UC, or lowering slow P95, makes gate more conservative. The printed winner and gate make the promotion decision explicit and auditable. This gating pattern gives you a repeatable promotion step. You can tune the weights to match your product priorities. For example, a chat assistant might prefer lower latency, while a legal assistant favors correctness. The gate check enforces minimum standards before automation shifts traffic. Next, we pick a runtime route when budget is tight. This snippet chooses a runtime fallback route under budget pressure. The list routes contain simple profiles with P95 latency, success probability, and cost. The function pick first filters candidates that satisfy SLO-OK and SLO P95, ensuring only compliant routes are considered. It then switches the sorting key based on burn. When burn is high, it prefers lower cost first, then latency. Otherwise, it prefers lower latency, then cost. This lets you trade performance for spend during incidents automatically. Tightening slow UC, or lowering slow P95, shrinks the eligible set, making safer routes more likely. The printed route and burn show which path the system will take now. This decision lets you gracefully degrade. When your budget is healthy, you chase latency. When the budget is burning, you save spend and preserve availability. You can extend routes to include human-in-the-loop steps, cached answers, or simpler models, and the same selection logic keeps behavior consistent. Finally, we run a tiny policy engine that chooses allow, fallback, or page. This example runs a tiny policy engine for allow, fallback, or page. A short latency list yields P95, and the OK vector becomes a success rate. We approximate groundedness GT by measuring how many answer words appear in a simple source stock, a lightweight proxy for being supported by retrieved context. Using slow OK, we compute burn from recent failures. The function act pages when burn is high or groundedness is weak, otherwise falls back if latency or success drifts. Raising the P95 threshold reduces fallbacks. Increasing SLOK or lowering the groundedness cutoff makes paging more likely. The printed action with P95 shows the immediate operational decision. This tiny policy is a direct map to real operations. It shows how runtime telemetry and lightweight content checks can steer traffic between automatic answers, simpler fallbacks, or human review. You can replace the groundedness proxy with a retriever or a better citation check as you scale. Recap. What it is: a small, measurable pipeline that converts latency and success observations into SLOs, an error budget, and automated actions. When to use it: whenever you want predictable user experience from an LLM in production, especially during rollouts. One caveat: these heuristics are only as good as your SLIs and the proxies you use for quality. Next step: tune your SLOUC target across 1 week of traffic to see how burn behaves. Then tighten or loosen it to match your risk tolerance. That single sweep will tell you whether to change the gate weights or adjust fallback preferences. If practical AI engineering helps, subscribe and watch the AI engineering videos.